which has magnitude equal to 1. That is nothing but point of intersection between unit circle and polar plot, right? Next thing, this is how omega GC is calculated. Another thing is we need to locate what is omega PC. Okay. Now to calculate omega PC, we need to have the intersection with the negative real axis, because we need to have the angle to be minus 180 degrees, right? So in the S plane where the angle is minus 180 degrees, if you see the angle, this negative real axis is nothing but minus 180 degrees line, right? So now what we are supposed to do, point of intersection of negative real axis with polar plot is nothing but omega PC. Okay. So two things we have seen. The point on polar plot which intersects with unit circle is the point at which magnitude is 1, which gives you omega GC. And the point of intersection of polar plot with negative real axis gives you omega PC. Okay. Now let us go back to the slide. Here we need to learn a concept which is called as critical point. Now just now we have seen that we need to have the magnitude to be 1 and we need to have the phase to be minus 180 degrees. So there is a point in S plane which satisfies both the conditions. Okay. So the point that satisfies both the conditions can be plotted on in S plane, and that point is known as critical point. Now what that point is, magnitude has to be 1 and angle has to be minus 180 degrees, right? So when angle is minus 180 degrees, that means we certainly should have the point on negative real axis, because only this line corresponds to minus 180 degrees in S plane. Now on this negative real axis, the magnitude has to be 1, right? So the point minus 1 plus J0 corresponds to the point where both the conditions are satisfied, isn't it? So this point is known as critical point. I hope this is clear with you. Minus 1 plus J0, why imaginary part is 0? Because the point lies on the real axis only. The point should lie on negative real axis because angle condition should be satisfied, that is minus 180 degrees, and the magnitude has to be 1. So on negative real axis, there is only one point which satisfies this condition, that is minus 1 plus J0. So this point is known as critical point. We are going to need these concepts later on. Just try to remember these. All of these are available in the notes. You anyways, anytime can go back and refer to these parameters or concepts. Okay. Now we will see, if suppose we have a polar plot. Till now we have seen how to sketch a polar plot and then how omega GC and omega PC are located. Then what is the critical point? The criteria, now we will see the criteria which describes whether the system is stable or unstable from the polar plot. So please refer to the first line on the slide. If the critical point minus 1 plus J0 is enclosed in a polar plot, then the system is said to be stable. All of us know the dictionary meaning of enclosement, but we will see what is the technical contextual meaning of enclosement on the next slide. And if the critical point lies outside the polar plot, the system is said to be unstable. Okay. What is the significance of this? Suppose if you have a polar plot which encloses minus 1 plus J0, that means minus 1 plus J0 lies inside the polar plot. That means you still have a margin from the critical point to cross the polar plot, right? So when gain margin and phase margin both are positive, the system is stable, as we have also already studied in Bode plot. If it lies outside the polar plot, that means you have already crossed this point and there is no margin left with you for the system to be stable. In that case, the system is already unstable. Okay, so these two are the conditions based on which you can comment on the stability using the polar plot. Okay, so now what we will do is we will see what is enclosement, technical or contextual meaning of enclosement. what enclosement is, the point is said to be enclosed by a path if the point is at the right side while traversing a particular path. Okay. Now, I hope the meaning is clear to you. Just a minute. So suppose now you have this path. When we consider path, the direction is important and you are considering this point. Okay. So now when you are going from this direction and when you are moving in another direction where the point lies, initially the point lies in the left half of this plane. Sorry, left half of this path, right? So we can't say that this point is enclosed by a particular path. If you have this and then if you are moving in this direction, then we can say that the point is enclosed, because if we are moving in this direction, always the point will lie to the right side of the movement, right? So this is called as enclosement. Now the limitation, here comes the last point of this session, the limitation of polar plot, and why do we need to move to Nyquist plot. So this is an example which is given. Now take a look at the example. I have marked a critical point. Okay, suppose this is the critical point -1 plus j0. Now if you have this kind of polar plot, for some portions from when you are traversing this in this direction, for some portions the point will lie to the left side. For some portions the point will lie to the right side of polar plot, right? So there is no way or no means in which you can conclude or infer whether the polar plot encloses the critical point or not, and in turn whether it is a stable system or unstable system. So basically this is a limitation on polar plot, that there are certain polar plots where you will not be able to identify whether the critical point, or for that matter any point, is enclosed in a polar plot or not. In that case, it is difficult to comment on the stability, and this is the major limitation on constraint on polar plot, and because of which we moved on to Nyquist plot. Okay, so in this particular session we started with the definition of polar plot. Magnitude is plotted versus phase when frequency is varied. Then we have seen an example. Please take a look at the example. Magnitude and phase are calculated and then plotted against each other when omega is varied from 0 to infinity. Then we have revisited the definitions of gain margin, phase margin, gain crossover, phase crossover. Then we have seen how to locate omega GC, omega PC on a polar plot. Omega GC can be located on a polar plot as the point of intersection between unit circle and polar plot, and omega PC is point of intersection of the polar plot with negative real axis. Then we have seen the significance of critical point. -1 plus j0 is the point which satisfies both the conditions. Okay, so -1 plus j0 where omega GC is equal to omega PC, both the conditions are satisfied, angle is -180 degrees and magnitude is 1, right? So that point is known as critical point, which is used to comment on the stability of a polar plot. Stability of a polar plot depends whether the polar plot encloses critical point or not. If it is enclosing critical point, the system is stable. If it is not enclosing, the system is unstable. And here on this particular slide, we have seen the limitation where in some polar plots, some part, for some portion of polar plot, we can say that the point is enclosed. For some other part, we can say the point is not enclosed. So here it is very difficult or not possible to comment on the stability of the system that is given to us. And that is why we do not use polar plots for commenting on the stability. We move on to Nyquist plots. Please bear this in mind that Nyquist plots are basically polar plots. Using some different criteria, we can comment on the stability of such systems. And that criteria is known as Nyquist theorem, which we will be learning in the following modules. Okay, please have a look at these slides or notes that are given to you. And if you have any difficulty, you can get back to me easily. Okay, thank you.